Sections 3.1 and 3.2 are about some derivative properties that we've already talked about. Essentially, the power rule and its application, linearity and its application, and derivatives of exponential functions. Power rule, linearity, derivatives of exponential functions. So we just need a little practice with these things. Let's start with a function that's not a polynomial, but it's kind of like a polynomial in the fact that it's going to be a sum of some powers of x with some coefficients in front. And let's even make it a little trickier by making the first part be a fraction even. Ooh, it looks scary. Let's say that's our function, and we'd like to find the derivative. Do not use the limit definition of the derivative. That would be a very, 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 very unpleasant experience. I'm not even sure I could do it without making a mistake. We want to use derivative rules. Derivative rules are very powerful. We're very happy that we have derivative rules. Doing a derivative like this would be next to impossible without them. You need to break down this function into really a linear combination of powers of x. How? This is the most mysterious part here. Here we have a fraction, a quotient. Don't we need the quotient rule for those who've had calculus before? No, you don't, because you can break this function apart into pieces, essentially undoing some fraction addition, like that. If I keep the denominator the same in both fractions, I can break that fraction apart. Why? Well, think about going the other way. If I was adding these two fractions, they already have a common denominator. So the way to add fractions when they have a common denominator is just to make a new fraction with the same denominator, but you add the numerators, right? That's how you add fractions. Doesn't matter that they're functions instead of numbers. They're still fractions. All right, that's good. But we still have fractions here, don't we? So do we need that quotient rule that I was hinting at? No, you don't, because you can simplify these fractions into constants times powers of x. Here I've got x squared divided by x cubed. Subtract the exponents. 2 minus 3, -1. Square root of x is x to the 1/2 power. Subtract the exponents again. Put the 5 out in front. 1/2 minus 3. 0.5 minus 3 is -2.5. As a fraction, that's -5/2. Should be able to deal with fractions and not necessarily convert to decimals. 1/2 minus 3, getting a common denominator of 2, is -5/2, which is the same as -5/2. Bring that negative sign out in front. It is -2.5, but you should be able to deal with the fractions too. And then here I also have another x to the 1/2 being multiplied by x, which is the same as x to the first. Now add those exponents. 1 plus 1/2 is 3/2. I haven't taken the derivative yet, right? All I'm doing is rewriting the function in a way that's going to allow me to use linearity. This is a linear combination of powers of x, a constant times x to the -1 power, the constant being 4, plus another constant, x to another power, plus another constant, x to another power. That's called a linear combination. And linearity says that the derivative of such a linear combination, in this case, is going to be 4 times the derivative of that. Watch where I'm pointing. 4 times the derivative of this, plus 5 times the derivative of that, plus 6 times the derivative of that. 4 times the derivative of x to the -1. Now use the power rule. Bring down that -1 power. Subtract 1, -1 minus 1 is -2, not 0. Right? -1 minus 1 is -2. Do the same thing with the next term. Keep the 5 there, bring down the -5 halves. Subtract 1 from the exponent. -5 halves minus 1 is -7 halves. Same as -2.5 minus 1 is -3.5. If you use decimals instead of fractions, is it okay? Yeah, but work at using fractions. Okay. I know fractions can give people trouble even when you're in college. Okay. I know that from experience teaching. Even people in calculus in university still sometimes have trouble with fractions. You're not alone if you do. So practice. Plus 6 times the derivative of x to the 3 halves, bring down the 3 halves. 3 halves minus 1 is 1 half. Now, don't leave it like that, simplify. I could simplify it like this. 5 times -5 halves is -25 halves. I just multiply the tops. 6 times 3 halves, I can cancel the 2 with the 6 to leave a 3 times 3 is 9. I could leave it like that. That is fine. There are other ways you can write the answer as well. You could write it as -4 over x squared minus 25 to x to the 7 halves. And you could write x to the 7 halves if you like as x cubed square root of x. Think about that. 3 plus 1 half is 3.5, which is the same as 7 halves in the denominator for the power. Plus 9 square root of x. That's fine as well. Do you need to combine these fractions into one? You could. But to tell you the truth, if you do, you might make a mistake. In fact, you might have made a mistake going from here to here. For the purposes of the gateway exam, it's probably best to leave the answer like that. Hopefully, I did not make a mistake. Looking it over, I think I'm okay. This should be equal. I don't think I made a mistake. If you combine these fractions into one by getting a common denominator and don't make a mistake, it would technically be okay. For the gateway exam, leave it like that. For the purpose of homework, though, it's good to simplify for 2 reasons. One is it might help the grader grade your homework. Maybe 3 reasons. Secondly, it's good to practice a little simplification skills. Thirdly, and perhaps most importantly, when you simplify derivatives in certain ways, it can help you apply them. To figure out, for example, what the graph of this function looks like. Derivatives are useful for figuring out what graphs look like, especially when you simplify them. In this case, merging them all into one fraction is probably best to understanding how the derivative can help you graph the original. I'm not giving details on that right now, but that is probably best. Here's a non-example. What? What's a non-example? Here's an example that maybe looks like you could apply the rules I just showed you, but you really can't. Non-example. Non-examples are examples, but they're examples that show you can't do something instead of that you can do something. F of x equals, I don't know, x squared over x cubed plus 5 square root of x. Kind of looks somewhat similar to that problem we just did. So you might think, oh, I could just break this apart into 2 fractions and do the same kind of thing I did before. But no, not really. You can't break it apart into 2 fractions because the denominator is a sum instead of just one thing. In this problem, the denominator was just one thing. You can break it apart to this over this plus this over this, like I did right there. Can't really do that here because the numerator is just one thing and the denominator is the sum of 2 things. I mean, even if we had 2 things on the top, x squared plus x or something, Yes, you'd be able to break it into two fractions in that case, but the denominator would still be the sum, and you wouldn't be able to simplify that. Is there any other way to simplify? You could try factoring out a square root of x on the bottom and doing some partial cancellation. And maybe if you allowed negative exponents, you could even factor out an x squared out of the bottom and cancel with the top. But that's still not much help because you'd still have a sum on the bottom. So it's not so clear what the derivative should be here. F prime of x equals big question mark. The rules from section 3.1 and 3.2 are not going to be helpful for this kind of problem. And recognizing such non-examples does sometimes come up in homework problems to say, can I use the rules in this section for this kind of problem or not? In this case, the answer is no, you can't. Does that mean the derivative does not exist? No, it does not mean that. It means we just don't have the rules yet. What rule do you need? You need something called the quotient rule. This is the quotient of two functions. Quotient is synonymous with fraction or ratio. You need that quotient rule, but we haven't talked about that yet.
So if this does come up, will we use that definition?
No, if it's a problem like this for the homework, it would be a problem phrased as, can you use the rules for this section to differentiate this? If yes, do so. If no, say why not. And here you'd say, well, I can't break this apart into a linear combination of powers of x for section 3.1. So I've just looked at a couple examples. You need more practice. These examples, I think, are good examples to talk about. But you're going to do homework problems that involve more practice. You need some practice. We're going to start practicing for the gateway this week by working on the homework. In part, the homework is to help you practice for the gateway. That exam where you're just taking derivatives. And you need to get 6 out of 7 exactly right to pass. You do get more than one chance to pass. It's kind of like that old exam that I had trouble with in grad school. But we also want to be able to do some problems from section 3.2, derivatives of exponential functions. I've already talked about this fact as well. d dx, the derivative with respect to x of b to the x, where b is a positive base not equal to 1. Actually, this rule, it works even if b is 1, but we don't typically think of it that way, is natural log of b times b to the x. Remember that from a couple weeks ago? In the case where b equals e, the number e, this becomes natural log of e times e to the x, but natural log of e is 1, so this simplifies to just e to the x. And that fact right there, the most important special fact in calculus for a special function. And fortunately, it's also the easiest to remember. The derivative of e to the x is itself. But if you've got some other base, like 2, if it's 2 to the x, you get natural log of 2 times 2 to the x. If the base were a fraction like 1/3, if you were trying to differentiate 3 to the negative x, you'd want to think of that function as 1/3 to the x. At this point in the semester, very soon, you will not do what I'm showing you. That's the same as natural log of 1/3 times 1/3 to the x. Don't stop there for this kind of problem. Although if it were on the gateway, I'd say you could stop there. But it is good to realize natural log of 1/3 is the same as natural log of 1 minus natural log of 3. And 1/3 to the x is the same as 3 to the negative x. This is 0. So the best way to write the final answer is negative natural log of 3 times 3 to the negative x. Is the best way to write the answer. Though this is not wrong. When we learn another rule called the chain rule, starting on Friday this week, we will not use this method to differentiate this. We'll use this thing called the chain rule that'll get us to this answer pretty much right away. And we won't have to do these intermediate steps. But for the moment, for section 3.2, you should do these intermediate steps. If you've taken calculus before and you say, hey, I know the quotient rule, product rule, chain rule, don't use them now. You're not allowed to. Okay, you've got to go through this process like everybody else and not work ahead. I mean, it helps you appreciate those rules later on anyway, so it's worth doing. Can any rule be used on the gateway? Yes, on the gateway, but for the homework due Wednesday, use only these rules I'm showing you. Sometimes things get a little weird and we throw curveballs at you, like find the derivative with respect to x of, say, x to the pi power plus pi to the x power plus, oh, how about x to the e power plus e to the x power? A linear combination of 4 functions, so I take the derivative of each one of those and add those derivatives. The coefficients in this case are all 1s. It's a little weird though. You got to recognize that these two are power functions. X is in the base. The exponents are constant. Pi and e are constants. We need the power rule for these. These two are exponential functions. X is in the exponent. The base is constant. So for the derivative of x to the pi power, I get pi x to the pi minus 1 power. For the derivative of pi to the x power, I get natural log of pi times pi to the x power. For the derivative of x to the e, I get e to the x to e times x to the e minus 1 power. And for the derivative of e to the x, I get e to the x. There's the answer. What rules did I use? I used the fact that I've got a sum of functions here. The derivative of a sum is the sum of their derivatives. That's a power function. Here I use the power rule. This is an exponential function. I use the derivative of an exponential function. There's a power function. I use the power rule. Here's an exponential function. I used the rule for derivatives of exponential functions. Okay, so that's how to do this one. Sometimes things can be tricky in other ways. The tricks are not just meant to throw curveballs at you for the sake of throwing curveballs, but to re-emphasize, do you know your algebra rules, for example? Here's another example of that. Take the derivative with respect to x of, oh, say, 2 to the x times 3 to the x. I've got the product of two functions here, and those who've taken calculus would be saying, hey, I use the product rule, but wait a minute, not allowed. So what do? It's a property of exponents that I've got one number to the x power times another number to the x power. That's the same as the product of those two numbers to the x power. That's not 2.3, that's 2 times 3 there. This is the derivative of 6 to the x. By the rule for exponential function derivatives, that's natural log of 6 times 6 to the x. Done. You can leave it like that. Can that be written in terms of base 2 and base 3? Yeah. We could do that. This is the same as 6 is 2 times 3. So I could do this if I wanted to. Hey, log of a product is the sum of the logs. And this, by the same property I used up here, is the same as 2 to the x times 3 to the x. And then I could use the distributive property to bring that through and get natural log of 2 times 2 to the x times 3 to the x plus natural log of 3 times 2 to the x times 3 to the x. Did I do anything wrong there? That seems pretty weird. No, I didn't. This is another form of the correct answer. And it would be the form you would get if you used the product rule, for those who've taken calculus before. But to tell you the truth, this answer is a bit simpler, right? So combining these into one power of x, one base to the x power, is actually a bit simpler in this case than using the product rule. So for the moment, you would do this and leave the answer like that. Question? Are you saying if you had to give explanations for each step, should you be able to do that? I don't think the book typically phrases that, but you should be able to show this work. If you had to give explanations, you'd say this is because of some algebra properties of exponents. This is because 2 times 3 is 6. And this last step is because of this rule for derivatives of exponential functions. Okay. Should be able to think about it graphically too. Why does the derivative of b to the x proportional to itself? If it's exponential growth, if you think about the slopes, they start out positive but small, and they become positive and large, just like the graph itself starts out positive and small and ends up positive and large in output. And if it's exponential decay, the slope is always negative, starts out negative and far away from 0 and heads towards 0. The derivative has to have a graph that is the same kind of shape but reflected. Not necessarily exactly the opposite of this, because you have this extra factor, natural log of b. The derivative of this is not necessarily the exact same graph, but it's going to have the same kind of shape, unless b equals e. Then it is the exact same graph. The outputs of the graph, the y coordinates for e to the x, are the same as the slopes at those points. On the graph of e to the x, this is y equals e to the x, and this is x equals 2. The y coordinate at that point is e squared, and the slope of the curve right there is also e squared, which is 6 or 7 something. 7 something, I think, for e squared. The y coordinate matches the slope for e to the x. That's what's so special about it. And that's why we use base e.